lighting calculations. So we've already looked at a lot of the geometrical data behind how we figure out where something should be on the screen using pipeline graphics. That is, we start in some kind of local coordinate frame, we move that out into the global coordinates and back into the eye coordinates of the camera, from where we can project things onto the near plane, which will then be positioned correctly on the screen. So we have the screen position in a sense of the vertices that we're sending through, but now we're going to look at something that really adds to the three-dimensional feel of what we're drawing. That is the color and lighting. So to begin with, before we go entirely into the math here and ideas behind computer graphics lighting calculations, let's just look at the idea of light, or the reality of light. So if we imagine real light as a ray just traveling at the speed of light towards something, a light source might emit endless rays of light in all different directions. Whenever a ray hits a surface, it can be reflected off it. It can lose some of its intensity. It can reflect partially. When it hits a matte surface, it'll scatter in all directions, but with less intensity. But if it hits a very smooth surface or a reflective surface like a mirror, it'll reflect straight into a similarly strong ray in a different direction. And then we have materials that absorb certain wavelengths, meaning that different colors affect them differently. So different colors affect different materials differently, and they reflect different lights. And in reality, this ray will reflect until it's completely lost all its intensity. And if you imagine just a light turned on in a room, it'll be reflecting off the walls constantly in every direction, kind of filling the room with light. You don't have a perfectly strong shadow on any side that is facing away from the light, and very strong light on everything that's facing towards it. Instead, it reflects off of everything in the room multiple times, even, astronomical number of times, and fills the room with light. So this absolute real behavior of light would be so computationally heavy that, especially in real-time graphics and in pipeline graphics, we simply couldn't simulate this properly. So we need to simplify light. So rather than just having one type of light that scatters in different ways depending on surfaces, we split the light into three types of light. So we have light that reflects, which is specular light in computer graphics. We have light that scatters, so something that looks like it's landing on a matte surface, and that's the diffuse part. And then we have light that fills the environment, which is ambient, and it doesn't matter exactly how it's facing the light. It's just the part of the light that will scatter all over the place and fill in the room. And these types of light have their material counterparts. So any object that we're drawing, or that we're sending through the pipeline, will have to have some material defined. And the material will also have a diffuse part, that is the matte part that scatters light. It'll have its specular part, that is the smooth part that reflects light. And it'll have its ambient part, that is how much of this light that fills the room affects this particular material. And then it's also worth noting that you can set up an intensity for the material that is where lights have no effect. It's often called emission, basically the amount of color that will be on this object regardless of any lights in the room. It can be used either for things glowing in the dark, or just to make sure that there is some intensity on all objects, so they're never absolutely dark. But you can use the ambient for that as well. So we'll look a bit at how we work with this. And now we get to the calculations themselves. So what we looked at was the fact that we have specular light, we have diffuse light, and we have ambient light. And then we have diffuse material, ambient material, and specular material. And what we have here is a formula that simply says the final intensity of some color, that is the value that will be put on some color in for this vertex or for a certain pixel, will be the ambient intensity of the light multiplied by the ambient value for the material that we're working with. Then we add to that, and it's worth noting that all of these numbers here will be numbers somewhere between 0 and 1. So each factor here, or each part of this formula here, can never be higher than 1 or lower than 0. So with full intensity on everything, we'll end up with 1 in each part here. So in ambient intensity of the light times the ambient part of the material plus the diffuse intensity of the light times the diffuse value for the material times a factor here that's called Lambert, and we'll look at how we calculate that later on, but it has to do with angles between the normal to the surface, that is the facing of the surface, and the direction from the surface to the light. Then we have this shiny part, specularity. So we have the specular intensity of the light times the specular value of the material times another factor here called Phong, which is again a number between 0 and 1. And this one has to do with the relation between not only the facing of the object and the direction to the light, but also the direction to the camera and how the light will reflect into the eye that's watching it. And then we have this shininess factor here, F, which is a power that is put on Phong here, simply in order to kind of maximize the shininess or the glossiness, or change the glossiness of the kind of specularity, to make sure that different materials can have kind of different sizes of the intense shine point. We'll look at how that affects the actual outcome later on. But in order to be able to calculate this, we can see that the intensities of the light and the values of the color are simply something that we will have to define and send into our shader for it to work with. But the values Lambert and Phong need to be calculated, and so we need to look at what basically what vectors and what geometrical data we need in order to calculate those. And so we have a simple image here where we imagine we have this horizontal line here, which is the surface. So the surface can be facing anyway, and each vertex that we send through the pipeline will have an associated normal, and that normal is basically the direction that the object is facing, or the surface of the object is facing at this point. So we have a normal, which is the way the object is facing. Then we have the position of the light and the position of the eye, and by subtracting the position of the vertex that we're doing lighting calculations for from each of these, we get these vectors S, which is the direction to the light, and V, which is the direction to the camera, or the direction to the eye. S in some cases can also be set, like we can have a directional light. We don't have to have a positional light and then calculate S. We can simply send S in there and say, for this light, it should always be calculated as if the light is in this particular direction. You can imagine this for sunlight or for light that is so far away that it's basically in the same general direction wherever in the scene we are. And also V in some cases can be simplified, especially if we're calculating this in eye coordinates. We can simply use a vector 0, 0, 1 instead of actually using a vector pointing at the camera. But this will, in the end, especially for things that are close by the camera, look significantly worse. So it's best to have actual positions of the camera and positions of the lights and calculate these vectors here. So once we have these vectors, we can go ahead and find out certain certain relationships between them and use them to calculate the light. So for diffuse light, we calculate the value Lambert, which is basically something, if we look at the picture again, we need something that kind of tells us the or how these vectors here are oriented relative to each other. So we can imagine we're not looking at the I or the V vector at all now. We're just saying if light were to shine straight onto the surface, we would get a lot of intensity. So if S and M were parallel, we'd like to get the intensity 1. If, however, the light is way over here and S and M are perpendicular to each other, we can kind of say the light is shining, it's kind of missing the surface. It's going straight past it, and so we'd like to get the intensity 0. And also for anything that's on the other side, we'd like to get the intensity 0 as well. So from here all the way to here, we'd like to get the intensity 0. Then we need a gradual change up to here, or from here and up to here. But if we have the light shining straight onto the surface, we want to get the intensity 1. So if we simply take these vectors and find, we don't even need to find the angle between them. We can find the angle's cosine, and that can be calculated fairly cheaply. And we know that this is 1 when the vectors are parallel and 0 when they're perpendicular to each other. So if we look at how this looks, the cosine itself is calculated like this. We have the vector S, which is the direction to the light. We have the vector M, which is where the vertex is facing. If we simply take the dot product of these normals, or sorry, of these vectors normalized, then we get the cosine of the angle. So if we're not sure that we're getting unit vectors in, we have to make sure that we divide this result by their length. So we calculate the lengths. We don't need to actually normalize them beforehand. That's more expensive because then we have to divide by each coordinate. Instead, we take the dot product and get one single number, multiply these together, and then divide by the number. So it's a bit cheaper doing it afterwards. Anyway, so what we have here is this number. Unless it's less than 0, then we just get 0. So if the cosine is giving us a negative number, it means it's on the other side of the surface relative to the normal. So this here will give us the angle between them, or the cosine of the angle between them, and so give us the intensity. And that's the function Lambert. And in our formula, we multiply that with the diffuse intensity of the light and the diffuse value of the material. So we're basically taking, for a specific color, we do this basically for red, green, and blue independently. So we take the value for that color of the diffuse material, we take the value for that color of the light intensity, and we multiply that with this intensity, which basically tells us how directly onto the surface the light is shining. And this gives us diffuse. And the reason this emulates light that scatters is that we're only looking at how the light hits the surface. The camera itself could be anywhere and it has no effect. So imagine that it hits the surface and then scatters equally in all directions with this intensity. So Lambert is giving us that intensity. Wherever the camera is, it'll get the same intensity of the diffuse part. Specular light, however, then we're taking into account where the camera is as well. So if we go back to the picture, you can see here that if we imagine that we take the light coming from here and reflect it around the vector M, meaning that it'll go somewhere up here, then we have a vector here, which is the reflected vector, light vector reflected by the normal itself. And if we take the angle between that reflected vector and the vector v, which is pointing towards the eye, we get kind of how close this light is to reflecting straight into the eye. So if we imagine the eye was a bit higher in this image and v was right here, and s would reflect into a vector that's parallel to v, then those two vectors would be very close to parallel, and they'd give a very high cosine between them. So we take the cosine between vectors again, except we're not taking the cosine just between the normal and a single vector, but instead we're imagining this reflection. Okay, this is not exactly what we do in the end, but we're gonna look at how this would look. That we simply take this reflection and say we calculate the reflection as if S is being reflected around M, and then we take the vector V, which is this vector, and the resulting vector R, and we take the cosine between them, which if the light reflects straight into the eye, straight into the camera, we're going to get full intensity, the intensity 1. If, however, the light is reflected sort of 90 degrees from that, we get 0. But what we add to this, if we look at the formula here, is this this power here. So the reason we have this, if we're simply the power of 1, and we'd calculate Phong, we'd get a really big area, a very big gradient. Like we'd have the full intensity here, and then the intensity would gradually go down. And if we imagine this surface kind of being round here, so the normal is changing, or we're taking the camera around, the shine spot that we end up with would be really big, just as big as the side of the object that's being well, lit up by the diffuse light. So by putting this power here, because these are always numbers between 0 and 1, this is not making the number bigger, but in fact smaller. So what it means that if we put a high number here, like to the power of 30, we still have the fact that if the reflected vector and the vector v are exactly parallel, we still get full intensity. But as soon as the angle just gets a little bit bigger, we get something that's a little bit lower than 1, and when we put that to the power of 30, we're really diminishing that. So we get full intensity right where the reflection is the brightest, but then it drops off very quickly. So the higher the number f, the faster the intensity drops off in the specularity. So in effect, if we have just a sphere, and we'll get this little shine spot, the higher this number here, the smaller the shine spot will be, and it'll look more glossy, it'll look more like metal or very shiny plastic. But if we have a very big shine spot, it'll look all the more diffuse and all the more kind of scattery light. Anyway, so specular light, we imagine it like this, but what we actually do in the end, since calculating this vector r, this reflected vector r, would be really expensive, instead we want a less expensive way to do this. And actually, if we look at this, we're taking the half-wave vector, we don't even need to divide by 2 here. We don't need to multiply by half, because in the end, we're normalizing the vector anyway. We're taking the length of it, so it doesn't matter what the length is to begin with. So this is just a scaling factor. So you could just as well say the half-wave vector h is simply s plus v. That's good enough for any calculations. And if we look at that in the picture, what we're doing is we're taking the vector s and the vector v, and we're adding them one to the other, and what we get is a vector that's halfway between them. So imagine if this vector ends here and this one ends here, the vector that would end right between them would be the halfway vector. So h will be somewhere here, and then instead of taking the angle between h and either v and s, we take the angle between h and m, saying if the halfway vector is such that the normal is right parallel to that halfway vector, then the light s would reflect straight into the eye, because the halfway vector is kind of the vector that would reflect the light straight into the eye. So if m is parallel to that, we have full intensity. As soon as h is going further away from m, we know that the halfway vector that would reflect the light directly is getting further away from the vector that we're actually supposed to be reflecting around. And so we get more or less the same effect, except with cheaper calculations. So what we do in the end here is h equals s plus v, which is the direction to the light and the direction to the camera. And then we calculate Phong, which is the cosine of the angle between the normal to the surface and the halfway vector, which would reflect the light directly into the camera. And so again, if these vectors are parallel, we get full intensity, and as this drops off, we get a lower Phong, and then we add to that the power of f, the shininess, meaning that a higher power there will give us a smaller shininess spot, but a smaller but more intense spot of shininess on the object that we're rendering. So yeah, h is, well, here I say the average vector, but it would more be just the sum of the light vector s and the camera vector v. Don't need this half here. So h is the normal that would reflect s straight into v, and then we look at the angle between that vector and what we should actually be reflecting around. But in fact, we never actually do the reflection. We just make this imagined vector h, which would reflect the light correctly, and then check how does that differ to the vector m. So that's our specular light. And finally we have this, the entire specular part of the formula is the specular intensity of the light times the specular part of the material. That is how shiny or how reflective this material is, times Phong, which is again capped at 0, so we don't get negative numbers, and then that whole thing taken to the power of f before it's multiplied with these numbers. And f is, yeah, the shininess. Finally, in these lighting calculations, we have the ambient light. And the ambient part is simply the ambient intensity of the light times the ambient value of the material. And you can see that the normal and the direction to the light and the direction to the camera, none of these have an effect. So imagine this is just a light that fills the room and comes in from every side. This can be tricky to use, especially if you're using multiple lights and all of them have some ambient factor. It would be normal that each light kind of adds to the ambience, but sometimes it just gets a little bit difficult to handle when you're adding lights and everything kind of gets washed out in this ambient part, because you want the directional lights and the diffuse and the specular parts to really have their effect, but you still want some ambience. What is often done is, rather than taking an intensity, an ambient intensity for each light, we simply, in many cases, can just skip the ambient part of the lights and instead say we're just going to have one global ambience that we set. So we have one ambience, and that will always be multiplied with the ambient part of each material, but that'll only be done once, then not for each light. Then for each light, we do the part here, the Lambert part and the Phong part, but we skip this part for each light. So we do this for each light, sum that all together into one big intensity, so we make the sum of this for each light from 0 to the number of lights, add all this together, but this part we'll just take as one global thing. Very often OpenGL implementations will simply have the option of both. So you can add an ambient intensity to the light and to all materials, and then you can add a global ambient intensity as well. In some cases you'd just like to take all the light ambience and shut that out and just use the global ambience. In some cases though, you'd like it to look like that if you switch on and off a light, not only do its directional factors have an effect, but also like this ambience as well. So this is something you kind of have to decide on in your own shaders, how exactly you're going to do. But the Lambert part here, the diffuse part and the specular part, they're very important, and they really need to be implemented per light. So you need a couple of lights or a few lights that can be set in your shader, and each of them having a diffuse part and a specular part, and then you can really start seeing how the three-dimensionality of the light and changing colors of light and changing positions of light can add the true 3D effect to everything you're doing. The ambience, and especially the emission, which is basically, if we add the emission to this, we'd simply say we're adding the emission of the material. No part of the light has an effect, it's just we add the emission, like glow in the dark, just this color we add to the entire thing. Again, if you're using all of these things together, things might get washed out. So sometimes you actually use emission by itself and then have no other lighting calculations and just say this thing just emits light to a certain degree. For instance, for light sources you can use that. Then you can put a global ambience on to kind of keep that in check so that it doesn't just add up and add up and add up for each light, and then have Lambert and Phong implemented per light. That would actually be a nice way to set up your own light model in your shaders. Global ambience, Phong and Lambert for each light, and then have emission only on certain materials, and then not do the lighting calculations with them as well. But you can also mix all of this up any which way you want. So diffuse like this, only taking into account the direction to the light and the facing of the object itself, the normal. Specular light, building the halfway vector and then looking at the angle or the cosine of the angle between the halfway vector and the normal. And finally, and also taking the shininess factor here in order to make your specular point more intense and smaller for more shiny objects. And finally the ambient part, which is simply just the ambient intensity times the ambient value of the material added up. And this is mainly so that the lighting doesn't get too strong or kind of too rough. So if you're doing something that's supposed to happen in space, you might skip ambience altogether and just say if something lights up a planet from the side, only that side is lit and the other side simply disappears entirely. But if you're making lights inside a room, you kind of want something that fills in the room as well. So even though none of the lights that you have actually hit some side of some objects, you don't want them to become entirely black. You want some color to kind of seep in there, to creep in there. And this is what the ambience is for, just to add a little color to everything so that everything has its place in your final image, so things just don't go completely black or disappear. So that's it for the lighting calculations themselves, the math here, but we'll look at this in program and inside the shaders and everything later on, and actually look at the shader language itself and how we can kind of choose where exactly we do these calculations. Do we do them for each vertex, or do we take certain values for each vertex and kind of apply them to each pixel, or do or interpolate them onto each pixel and then do the lighting calculations for each pixel. We'll look at all that later. But for now, these are the lighting calculations themselves, the ideas behind them, and the way they're done in computer graphics, and which geometrical data we're using for them.